Hello everyone, my name is Kaiyuan Zhang. I'm here today to talk about our work on protecting the privacy of large language models during fine-tuning. This paper, which we call SOFT, is a result of a wonderful collaboration between Purdue University and Cisco Research. I assume everyone is familiar with the incredible progress in large language models. Their capabilities are advancing at a remarkable pace. This progress has made fine-tuning a standard practice for adapting these powerful general models to specific real-world tasks. And it is this fine-tuning process where our story begins. And this practice of using private data introduces significant privacy concerns. One of the main threats is the membership inference attack, which we call it MIA. The goal of an MIA is simple. Given a data sample, the attacker wants to determine if that exact sample was used to train the model. Initially, research focused on MIAs against the pre-training phase of the LLMs. However, pre-training uses enormous and web-scale datasets, and each data point is often seen only once. As a result, recent studies have confirmed that membership inference attacks against the pre-training data are largely ineffective. And given large-scale LLMs requires resources, for example, GPT-4 trains cost around 25,000 A100 GPUs and cost more than $100 million. The real danger and the focus of our study is in the fine-tuning stage. Here, the datasets are smaller and often contain sensitive information, such as personal data, medical records, or industry production code, and customer logs. The model is trained on this data for multiple epochs, which gives it a much greater opportunity to memorize it. This is a scenario where the privacy protection becomes essential. So, what's the underlying signals these attacks exploit? It comes down to a simple observation. Models tend to be more confident about the data they were trained on, and this is often reflected in a lower loss value. And an attacker main challenge is to distinguish whether a low loss is because the sample was a training member or simply because it's just a common and easy to predict sentence. And existing attacks use different methods to solve this calibration problem. And to create a strong and realistic evaluation for our work, we developed a powerful ensemble attack that combines these features from many of these methods and giving us a robust tool to measure privacy leakage. And with this strong attack method, we first set out to measure the extent of this problem. As this heatmap shows, standard full fine-tuning is extremely vulnerable to membership inference attacks, and the AUC score, which measures the attack success, are consistently high across many different types of data, such as code, academic papers, and general text. And critically, this problem gets worse with larger models and more training epochs. And perhaps most concerning, we found that even a single pass over the fine-tuning data is enough to cause the significant privacy leakage. Next, we asked a natural question. Do more parameter efficient methods, such as the LoRa, will solve this problem? The answer is that they can help, but they are not a complete fix. LoRa fine-tuning generally leaks less information than full fine-tuning, offering a better balance between the privacy and model performance. However, as you can see from the results, the attack scores are still well above random guessing. A determined adversary using a strong method like our ensemble attack can still successfully identify training members. And this told us that a more targeted defense was necessary. Motivated from the previous findings, this brings us to our solution, SOFT. The intuition behind it is simple. If the problem is that the model memorized certain data points too well, then let's just not show the exact original version of the data it is most likely to memorize. But we cannot just change the entire dataset. that would hurt the model's performance. So, how do we decide which samples to modify? We draw inspiration from work on influence functions. The key idea is that a small fraction of the training data accounts for a large portion of the privacy risk. And these are the influential samples, the ones that the model learns very quickly and assign a very low loss to. And these are the samples we need to protect. Here is how soft works in practice. It is a four-step pipeline that integrates directly into the fine-tuning process. And first, we do a warm-up pass. We train for one epoch to get a baseline understanding of how the model interacts with each sample. And then comes to the most critical step, influential data selection. In each subsequent epoch, we calculate the loss for every training sample. We compare that loss to a threshold, which we set as the average loss on a clean validation set. If a sample's loss is lower than this threshold, we flag it as influential and vulnerable. Next, data obfuscation. Any sample that was flagged is sent to a paraphrasing model like GPT-4 and replaced with a semantically equivalent version. The original safe data remain untouched. And finally, we fine-tune the model on this newly constructed dataset of safe and the obfuscated samples. By training on paraphrased version of this most vulnerable data, we prevent the model from overfitting on their exact text, which directly undermines the primary score, like the signal used by these MIAs. So does this approach actually work? This table shows the attack AUC scores across several models. To keep it simple, let's just focus on the average results of the archive dataset. The baseline pre-trained model is safe with an AUC of about 0.5, and standard full fine-tuning is highly vulnerable at 0.76, and the LoRa is better but still leaky at 0.59. Now let's look at soft. We bring the attack AUC all the way down to the 0.52. This is very close to random guessing, and we have effectively neutralized this attack. And importantly, as we detailed in the paper, we achieved this strong privacy protection with only a minimal trade-off in model utility. To summarize, what are the key takeaways from our work? First, we have shown that standard LLM fine-tuning presents a significant and practical privacy risk from membership inference attacks. Second, we propose SOFT, a novel defense that is built on the principle of selectively identifying and obfuscating only the most influential and vulnerable data points. Finally, our experiments confirm that SOFT is highly effective. It offers a practical and scalable solution that successfully balances strong privacy protection with high model utility. All of our code and data are available at the link provided. Thank you very much for your attention.